exchanger. This is 131 versus 151. As a result of this, your refrigeration effect increases. Since refrigeration effect increases, required mass flow rate reduces when you are using a regenerative heat exchanger. That is what you can see. Okay, and the required volumetric flow rate also reduces. That means basically you will be handling less amount of air. Okay, of course the penalty you will be paying is in the form of higher net work input because of the higher temperature at the compressor exit. Okay, you can see that net work input is much higher compared to the system without regenerative heat exchanger. As a result, the COP of the system with regenerative heat exchanger is less compared to the system without regenerative heat exchanger. So basically you have to make a trade off between the mass flow rate, the volumetric flow rate and COP, okay, and justify the use of regenerative heat exchanger, right. So this is a way to solve the typical problems in refrigeration and air conditioning. Okay, so based on this problem, I will give you a homework problem. You work it out. Okay, the homework problem is like this. You work out the above problem just by replacing air with helium gas. Okay, so rest of the data remains same. All that you have to do is you have to replace the working fluid with helium gas. Okay, and for helium gas the properties are like this. The specific heat Cp is given as 1.193 kilojoule per kg Kelvin, and specific heat ratio is 1.667. Okay, I will give you the answers in the next class for this problem. So the second problem is like this. This is a vapor compression refrigerant system. Problem on vapor compression refrigerant system. A problem statement is like this. A domestic refrigerator based on refrigerant R134A operates at an evaporator temperature of minus 23.3 degrees centigrade and a condensing temperature of 54.4 degrees centigrade. At these conditions, the required refrigeration capacity is 100 watts. Assuming a saturated single stage cycle and a compression process with an isentropic efficiency of 0.65. So this is the information given. Refrigerant is specified, temperatures are specified, capacity is specified, and the efficiency of the compressor is also given. From this information, we have to find out required refrigerant mass flow rate in kg per second, volumetric flow rate at compressor inlet in meter cube per second, quality of refrigerant at evaporator inlet, void fraction at evaporator inlet, actual power input to compressor in kilowatts, compressor discharge temperature, actual COP, and finally the cycle or second law efficiency. So this is the list the information given. Information given is like this. Refrigerant is R134A, refrigerant capacity is 100 watts or 0.1 kilowatts, and evaporator temperature is minus 23.3 degrees centigrade, and condensing temperature is 54.4 degrees centigrade, and the isentropic efficiency of the compressor is 0.65, and it is mentioned that it is a standard single stage saturated cycle. Okay. That means you have the 4 basic components. Since it is a standard cycle, you have the evaporator, compressor, this is the condenser, and this, as you know, is expansion device. And this temperature is specified, evaporator temperature minus 23.3 degrees centigrade, and this temperature, condensing temperature is specified 54.4 degrees centigrade, and it is a saturated cycle. So the exit condition, this is saturated vapor, and this condition, that is at the exit of the condenser, is saturated liquid. Okay, so this is the information given, and this compression is not ideal. So you have an efficiency for the compressor which is given by 0.65. Okay. So now using refrigerant property data, let us find out the required properties at various state points. Let me quickly explain how to find out the properties. Okay, what is that we know, and how do you find the rest of the properties? All that we know is, we know that the evaporator temperature, okay, TE is minus 23.3 degrees centigrade, this is given to us, and the condensing temperature TC is 54.4 degrees, this is also given to us. And we also know that the exit of the evaporator, that is 0.1, is saturated vapor, and exit of the condenser 0.3 is saturated liquid. So this is the information given to us, and it is also mentioned that the isentropic efficiency of the compressor is 0.65. Okay. What do you mean by isentropic efficiency of the compressor 0.65? That means the actual compression process 1 to 2 is non-isentropic, whereas 1 to 2 dash is isentropic. And from the definition of isentropic efficiency of the compressor, you can write the isentropic efficiency as isentropic work input divided by the actual work input. So, from energy balance, this is nothing but H2 dash minus H1 divided by H2 minus H1. This is given to be 0.65. Okay. So, this is the information that we have, right. So, from this information, how do you find the state properties, various enthalpies, temperatures at various points. So, let us begin with the saturation line, that means 0.1 and 0.3. Okay. This point is already fixed because we know the temperatures, and we also mentioned that this is a saturated condition. So, on the saturated line, specifying any one parameter is enough. Okay. So, once you say that it is saturated vapor and temperature is specified, we can immediately locate the point and find out what is the enthalpy H1 and what is the specific volume, what is the entropy, and all the properties can be obtained at this point. Okay. Similarly, all the properties at 0.3 can be obtained just from this temperature and the quality, because it is a saturated liquid. Okay. So, these properties also can be obtained directly from the refrigerant database, or if you have a pH chart, you can directly locate these points. Okay. And from the pH chart, you can find out what is the condensing temperature and what is the evaporating temperature once you know the condensing and evaporating temperatures. Okay. So, we know the pressures and we know the properties at 0.1 and 3. Now, how do you find the property at 0.2 dash? 0.2 dash lies in the superheated region. So, if you want to find the properties, you have to specify two independent properties. Okay. So, what are the properties we know? We know the pressure at this point. Okay. We know P2 dash. Okay. P2 dash is nothing but condenser pressure, which is the pressure at saturated pressure at 54.4 degrees centigrade. This is known to us. Okay. So, at this point we know the pressure. What else we know? We know that process 1 to 2 dash is isentropic process. That means the entropy at 0.2 dash is same as entropy at 0.1 dash. That means we also know the entropy at this point, because we know the entropy at 0.1. That means S2 dash is equal to S1. This is known. Okay. So, at 0.2 dash we know two independent properties, that is pressure and entropy. So, we can find out from these two independent properties rest of the properties such as temperature, enthalpies and all that. Okay. So, that is how you can find the properties of 0.2 dash. Once you find the properties of 0.2 dash, properties at 0.2 can be obtained, because at 0.2 we know that P2 is equal to Pc, which is known to us, and H2 is the enthalpy at this point. Enthalpy at this point is nothing but from the expression of isentropic efficiency, it is the inlet enthalpy plus H2 dash minus H1 divided by isentropic efficiency of the compressor. Okay. So, H1 is known to us, H2 dash is known to us also, and this is given as input. So, we can also find out the enthalpy. So, for this point, use the pressure data and enthalpy data and find out the rest of the properties. Okay. Now, coming back to 0.1 dash. 0.1 dash is nothing but the saturated liquid at evaporated temperature. So, straight away you can locate this point, because you know the temperature and you also know the pressure, and you know that it is in saturated condition. Okay. That means you have to locate this point on the saturated liquid line. So, you can find out enthalpy and all other properties. And finally, coming back to coming to the 0.4. Okay. 0.4 is nothing but the inlet to the evaporator, and what do we know at this point? At this point we know what is the pressure, and we also know the temperature. But can you find out from this pressure and temperature what is the enthalpy and rest of the properties? You cannot, because this is a two phase region. So, if you are fixing the pressure, temperature is automatically fixed. That means pressure and temperature are not independent properties in the two phase region. Okay. So, specifying both is meaningless. Okay. So, you have to, or useless. So, you have to specify any one and another property. What is that other property? That property is enthalpy, because we know that this process is a throttling process. So, for this process H3 is equal to H4. Okay. So, H3 is known to us, that means H4 is also known to us. That means at this point we know the pressure PE and we know the enthalpy H4. Okay. So, from these two properties you can find out the rest of the properties like entropy, specific volume and all that. Okay. So, that is how you have to find the properties at various points. So, it is always useful to draw the cycle on a pH diagram and list what the points you know, and have an idea of the different processes. Okay. Then you can straight away read the missing data points. Okay. So, using this procedure, this is the data obtained for various points. State point 1, which is the outlet of the evaporator or inlet to the compressor, temperature is minus 23.3 degrees centigrade specified, and pressure is nothing but the saturation pressure at this point is 1.148 bar, and we know that it is saturated vapor. So, quality is 1, which is known to us. So, if you are using this information from the pH chart or from refrigerant property database, you find that enthalpy is 384.5, entropy is 1.744 and specific volume is 0.169. Okay. Similarly, the data for other points at point 2 dash, which is nothing but the exit of the isentropic compression process, we know the pressure which is equal to 14.7 bar, and we also know the entropy, which is same as the entropy at point 1, that is 1.744. So, from the pressure and entropy data, we find the rest of the points, that is the temperature and enthalpy. Okay. Point 3 is the exit of the compressor and inlet to the expansion device. Here we know the temperature, which is equal to 54.4. So, the pressure is 14.7, which is the saturation pressure at this temperature, and we also know that it is saturated liquid. So, quality is known to us, that is 0. So, from the quality and the temperature, find out the rest of the properties like enthalpy and entropy. Okay, and then comes point 4, which is the exit of the expansion device or inlet to the evaporator. So, at this point, as I have already told you, we know the temperature and pressure, and we also know the enthalpy, because the enthalpy at point 4 is same as the enthalpy at point 3. Okay. So, using the pressure and enthalpy data, we find the rest of the properties, that is entropy and specific volume. And point 1 dash is the saturated liquid condition at evaporator temperature. So, we find out the enthalpy and entropy and specific volume at these conditions, and finally find out the actual temperature and enthalpy at the compression process, okay, at the exit of the compressor for the actual compression using the isentropic efficiency. Okay. So, this is how all the state points have been obtained. So, using this state point data, we will find the required performance parameters. One thing I would like to mention here is the enthalpy and entropy values may vary from database to database, okay, because if you remember, enthalpy and entropy are generally defined with reference to a particular datum. Okay. If the datum is different, then these values can be different. Okay. Whereas the rest of the properties will be same for all the property databases or all types of pH charts. Okay. So, you need not worry if the enthalpy and entropy values are different from source to source, okay, because in our calculations ultimately we will be requiring the enthalpy difference or entropy difference. Okay. Since you will be using the differences, the reference enthalpy or reference entropy really does not affect the final answer. Okay. So, now we know all the points. So, we find out the mass flow rate of refrigerant, apply the energy balance across the evaporator. From the energy balance, we find that mass flow rate is equal to QE divided by H1 minus H4. QE is known to us, this is 0.1 kilowatt, and H1 and H4 have been obtained from the refrigerant database. Okay. So, this will give us mass flow rate as 9.434 into 10 to the power of minus 4 kg per second. And volumetric flow rate at compressor inlet is nothing but mass flow rate into specific volume at compressor inlet, which is known to us. So, you find that volumetric flow rate is 1.594 into 10 to the power of minus 4 meter cube per second. And then quality of refrigerant at evaporator inlet. So, what do we mean by quality? We have already defined the quality. Okay. So, quality is at evaporator inlet is at this point. So, quality at this point is defined as mass of vapor divided by total mass, that is mass of vapor plus mass of liquid. Okay. You can show that this is equal to H4 minus H1 dash divided by H1 minus H1 dash. Okay. This is also equal to, you can write this in terms of, for example, specific volume, that means V4 minus V1 dash divided by V1 minus V1 dash. That means the quality can be expressed in terms of any intensive property such as enthalpy or specific volume or entropy. Okay, that is what is required. Since we know the enthalpies, we let us write this in terms of enthalpies. We know the enthalpy at 0.4, this is known because this is equal to H3, and H1 dash is known and H1 is also known. Okay, so we use that expression to find the quality. So, quality is found to be X4 is equal to H4 minus H1 dash divided by H1 minus H1 dash, which is equal to 0.5072. Okay. Then void fraction. Void fraction is defined as the volumetric flow rate of vapor divided by the total volumetric flow rate. So, the difference between quality and void fraction should be clear. Quality is in terms of mass flow rates and void fraction is in terms of volumetric flow rates. Okay. So, the volumetric flow rate can be expressed by multiplying the mass flow rates into specific volumes. So, if you do that, you find that the expression for void fraction is given like this: phi 4 is equal to V1 into x4 divided by V1 dash plus x4 into V1 minus V1 dash, and we know all these specific volume from properties. So, you find that volumetric flow rate is 0.9597. That means more than 95% of the volume is occupied by the vapor. And actual power input to the compressor, as I have already explained, is nothing but isentropic work input divided by the isentropic efficiency. We know the isentropic work input, which is equal to mass flow rate into enthalpy difference for the isentropic process divided by the isentropic efficiency 0.65. So, if you substitute these values, you find that the actual power input is 0.07736 kilowatt or 77.36 watts. Okay. Compressor discharge temperature. Discharge temperature can be obtained because we know that at the compressor discharge the pressure and enthalpies are known to us. So, using the pressure and enthalpy data, we can find out the compressor discharge temperature, and this is found to be 89.97 degrees centigrade. Okay. So, finally, we have to find out actual COP. Actual COP is defined as QE by W actual. QE is 100 watts and W actual is 77.36 watts. So, you find that actual COP is 1.293, and the cycle efficiency is COP actual divided by COP Carnot, and COP Carnot, as you know, is nothing but evaporator temperature divided by condenser temperature minus evaporator temperature, and all the temperature should be expressed in absolute scale, that means in degrees Kelvin. So, if you are writing this in degrees Kelvin, you find that COP Carnot is 3.216. Okay. So, from this you find that the cycle efficiency is 0.402. Okay. So, this is a very simple problem, and the whole idea of working out this problem is to show how properties at various state points can be obtained, and how the required performance parameters can be obtained by applying proper energy balance equations. Okay. So, let me explain the third problem. The third problem is another simple problem. This is a saturated single stage cycle and a SSS vapor compression refrigerant system based on refrigerant R134A operates between an evaporator temperature of minus 25 degrees centigrade and a condenser temperature of 50 degrees centigrade. So, evaporator and condenser temperatures are specified, and assuming isentropic compression, we have to find COP of the system, find work input to compressor, find area of superheat horn, and finally find the throttling losses. Okay. And assume that the isobar at condenser pressure to coincide with saturated liquid line. So, this is the information given to us. Okay, this is a standard vapor compression refrigerant system. Here it is convenient to represent this on TS diagram. So, you can see that on TS diagram cycle 1, 2, 3, 4 is your SSS cycle. Okay. So, 1 to 2 is your compression process, 2 to 3 is heat rejection in the condenser, 3 to 4 is throttling process, and 4 to 1 is isobaric isothermal heat extraction. Okay. And if you remember from our earlier discussions, the heat loss due to superheat horn is given by this. Okay. That means area 2 2 dash 2 double dash. This is the loss due to superheat horn, and loss due to throttling is given by this area. Okay. And if you are assuming that this saturated liquid line coincides with the isobar at this, that means it coincides with the isobar at PC, then this is also equal to throttling area. Okay. That means throttling area is either 1 dash 3 4 dash, which is equal to area CD 4 4 dash. Okay. So, we have to find out these two areas. Before finding that, we have to find out the state points at various locations, that means 1 2 dash 2 etc., and we know this temperature to be minus 25 degrees centigrade, and this is to be 50 degrees centigrade. So, we can find out this evaporator pressure and condenser pressure PC, because they are the saturation pressures at these temperatures, and we know that this is a saturated cycle. So, we can find out the data at point 1, which is the outlet of the evaporator, and inlet to the compressor, which is in saturated vapor state at evaporator temperature. Similarly, you can find out the properties at point 3, which is the exit of the condenser which is in saturated liquid region. So, these 2 points we can easily obtain. And point 2, at this point we know the pressure, okay, pressure is equal to condenser pressure. So, we can find out this, and we also know that this is an isentropic process. So, S2 is equal to S1. Okay. So, you can we know completely about point 2. So, you can find out rest of the properties. And point 2 double dash, you can see that this has a temperature same as the condensing temperature. That means T2 double dash is equal to 50 degree centigrade, that is known, and we also know that S2 double